tous. I'm going to stick to broken English. And we're going to talk about reinforcement learning. So how many of you know something about reinforcement learning? Okay, so you can sleep basically during the first half, at least. For the other, I'm going to try to give you an idea what it is, and then discuss some new results. So if you look at the menu, we're going to spend most of the time introducing what is reinforcement learning, and then I'm going to describe 3 results that have been obtained by a student of mine, and that will be it. I hope I will be able to do this in 40 minutes. So what is this reinforcement learning story? It's related to something that we can call sequential decisions. Often, when we think about machine learning, we think about the art of making single decision, making prediction of something. It turns out that in the real world, often when you take a decision, there are consequences. The world is changing, and you cannot rely on the IID assumption that is often there in the classical machine learning setting, the supervised learning one, for instance. And that's exactly what we're going to try to tackle. So we're going to think of a situation in which the final result is not due to a single decision, but to a sequence of decisions. What I mean by that, once again, the fact that when you make a choice, when you take a decision, you're going to have consequences. And you need to take into account those consequences to know whether this is a good or bad thing. As I've said, this is different from the supervised learning framework in which you have an immediate feedback. As soon as you make a decision, you're supposed to know whether this is good or bad. At least if you wait enough time or you ask someone, you can assign a performance to each decision. That's not going to be the case here. The whole sequence of decision will be important. It turns out this is easier somehow than unsupervised learning, in the sense that we're going to define the goal in a very specific manner, so that can be related to optimization one way or another. That was the whole plan. We're going to restrict ourselves to a simple model, as often in math. So here, we're going to talk about sequential decision as a way to choose actions, those 80 here, depending on some information. And the information will be denoted ST, the state, in all the talk, at least I hope. So we're going to act depending on the state of the world. You can imagine that each time we're going to act, we're going to receive a new state of the world and so on. And the way we're going to measure the quality of our action is through a very specific mechanism called a feedback, which is going to be measured by a scalar reward that we're going to receive at each time step. So I mentioned a lot the idea of actions, and you can imagine that the whole point is to pick those actions as well as possible. So maybe I've got a strategy in mind, and I want to know whether this is a good or bad one. That's one kind of question. But probably the most interesting question is, can I do better? Or ideally, can I find the optimal way of choosing this action? This is very broad, very generic, and most of the time we're going to restrict ourselves to a simpler setting that we can model in an efficient way. So here I've talked roughly of the environment, the state. I'm going to be much more specific. I'm sorry. I'm going to rely on a Markovian description of the world. Don't worry, I'm going to describe it again in a few slides. Very specific way of thinking of the world. Probably not true, but sufficient to do some analysis. And what I've mentioned that we've got a feedback through a scalar. Here I'm going to be much more explicit. the way I'm going to assess the quality of my decisions is going to be through the sum of those rewards. So we had something which was not very specific, and here we're going to be very specific. Still have the same question. Can I assess the quality of a policy, way of choosing the action, and can I make it better, and I define the optimal one. If I'm here, I'm in the world of probability. A Markovian model is a probabilistic object. I know everything about the world, and I'm trying to find what is the best choice within this world that I know perfectly. If we move to reinforcement learning, that's exactly the same modeling, but we are relaxing the assumption that we know the world. The only thing we have the right to do is to observe the world through interaction. So we can play, we can observe the world, and still we want to know whether we are doing something good or not, and still we want to find a better policy, a better way of acting, and ideally an optimal one. Very classical setting in modeling. We start by a rough ID, move to a strong, well-defined model, that probabilistic one, and then if we are missing some information, because we cannot observe everything in the real world, we have a second problem that we really want to tackle. Maybe some of you have read something about optimal control. That's basically the same question. At least if we think of discrete optimal control, that's exactly the same thing. In reinforcement learning, we want to maximize a reward. In optimal control, it's very different. We want to minimize the cost. But you can see that basically the same thing. On that related setting, stochastic algorithm, stochastic search, in which you're trying to find the expectation of something, and regret, in which you don't want to minimize the sum of the risk, but the sum of an expectation. The tool that we're going to see or we're going to use are similar in those settings. So what are those Markov decision processes? It's probably the most simple model you can imagine if you want to deal with a situation where you have an environment having a certain state, feed to this environment an action, so we want to act, and receive a new environment. As I said, I'm going to try to... At each time step, so this is a discrete time world, we know everything about the world, quite a strong assumption, but let's assume that's okay. We have a pool of action in which we can choose one. We feed this information to the environment, and we receive some new information. Two types of informations. First, the reward that we're going to use to measure the quality of our decisions. And then a new state of the world, which should depend on the action. What kind of model can we make of this? A lot. If we stay to the probabilistic world, we need to define the probability of reaching a new state and receiving a new reward, giving the past. And here, we're going to use this very strong Markovian hypothesis that this law depends only on what we are doing right now. So everything will depend only on the current state and the current action. No memory at all. Probably an oversimplification, but I'm pretty sure that many of you that have been dealing with time series or discrete events have used this assumption. Very convenient. basically the only one with which we can do a lot of math. I'm going to add a further assumption, which is slightly more than technical. I'm going to assume that everything is finite. So the set of state, the set of action, and the set of rewards. The main game is that we can write sums instead of integral. That's going to be really a detail of the story with respect of the reward. Each time you see a reward that could be continuous, basically any law, provided it's bounded, will be okay. You can move to continuous state by working well, but moving from a discrete set of action to a continuous one is much more challenging. That said, this is a very classical setting, so we're going to start with this one. I'm going to be slightly more specific, so I've said that I'm going to measure the quality through what is called the return, the sum of the reward. And if you look carefully, I've added some strength factor in front of the reward. I'm going to multiply the reward by a discount that depends on the distance from the past. And the only reason I'm doing this is for this object to be well defined. This is an infinite sum, a series, and you know that it will not be well defined. Here, if I'm putting this assumption, this object is always well defined, so I can work with it. For this talk, I'm going to focus on what is called a discounted case, in which this gamma is going to be strictly smaller than 1, so that everything is well defined. If you want to go deeper, you can relax this assumption, but you had to add much more complexity to the analysis. Last thing I want to stress is I'm going to rely a lot on a very complex observation, which said basically that up to this gamma factor, what we're going to gain from now is what we're going to gain right now, the reward, plus what we're going to gain in the future. Not very clever, but that's going to be very important in the analysis. And then I can define what is a policy. That's the way I'm picking the action given the state. I need to define a few objects. The value function. This is the state value function, not a value function, which is the expectation of the gain starting from a certain state, and so on. So on is the state action function, where I'm going to condition with the state and the action. And the question I was asking at the beginning, am I good? Can I do better? Can be framed as policy evaluation. Given a policy, what is this value function? What I can expect starting from a certain place. And the second one, what is the optimal policy? Maybe the optimal one is one which is better starting from any space, any state. Not claiming that those objects exist. Not obvious. It's true, but you have to work. And what is interesting is this is not something new. It can be traced back to the 50s and even during the Second World War. It's really related to operational research, the idea of optimizing a decision when there is a sequence. And for those of you who have done control, you can translate everything I'm going to say in the vocabulary of control, just a matter of changing the sign, because we're going to maximize the reward when you're going to minimize the cost in control. So what can we do? First, we can try to solve the first problem. I know the policy, and I want to know whether I'm good or not. I need to compute this value function. And it turned out that there is a key property which showed that the value function is the solution of an equation. this Bellman equation, which is here. It seems very complex, but it's nothing but saying that I can expect, starting from a state S, is what I'm going to receive from this state, plus what I'm going to receive afterward. That is, we can find this value function by solving this system. And this is indeed a way of solving this problem. You write down this linear system and you solve it. Turned out that there is a slightly different path, which is going to be much more useful in the reinforcement learning world, in which we don't know those transition probabilities that are appearing everywhere here. By solving this equation through a fixed point algorithm. So here, if you look at this equation, we mean that V pi is equal to the image of V pi through a linear operator. This is a fixed point equation. And it turned out that this operator here, that we know explicitly, is a contraction for the subnorm. Hence, I can solve this system by iterating this application. This is called dynamic programming, because basically it's betting on the fact that if I have a good estimate of what's going on in the future, I'm going to have a better estimate of what's going on right now. So we are propagating the information from the future to now. Can we improve the policy? Don't want to look at the exact result, but the answer is yes. There is a way to make a policy better whenever you have one. And the idea is funny, somehow, and quite intuitive. If you're like me, you are a bad chess player. You're just looking at the position, trying all of the policy possibilities and seeing whether it seems good or not. And that's exactly here what you can do. And you can prove that this is a good idea. You can look at what's going on if we play a specific action here, and then play using the current policy. And you can prove that if it was better to change a single action and then follow the rest of the time the current policy, it was the better choice from the beginning. Justification of this bad chess strategy here. You have proof of the convergence and everything, but that's not the point. And there is another way to look at this problem and to go back to the fact that instead of enhancing a policy, maybe I may want to find directly the best one. There is an equation which is somehow equivalent to the linear one that we've seen, which is called the Bellman equation. It's almost linear, except there is a max. So we move from the world of linear equation to the world of linear programming. There are solvers for those linear problems, but still we can show that this operator is a contraction, so we can rely on the idea of applying this operator several times to obtain a good solution. So in the MDP world, we've found a way to find the best solution and a way to obtain the best solution. And this is an idea that you're going to see everywhere. We're going to, most of the algorithm, we're going to maintain two estimates, an estimate of the quality of the policy and a way to enhance it one way or another. It's very efficient, but it's relying on a very strong assumption. We know the transition probabilities. We know the world. This is not realistic in many applications. So we need to move to the reinforcement learning setting. And that's basically exactly the same thing, except that you don't make the assumption that you know the transition probability. You only observe the result of your action. So it's slightly different, for instance, from classical data collection. Here you have the right to act, much closer to the bandit setting that we're going to see this afternoon, if I'm correct. But still you have the same question. Can I know whether I'm doing good or not? Can I do better? And then you have other questions. Can I imitate what I see? Can I guess what is the reward given what I see, and so on? So a huge field of question within this specific problem. So here, because we're running short of time, I'm going to focus on the prediction planning point. What can we do? We cannot rely on the probability formula that we've seen. So we cannot rely on the solving those linear equations or this linear programming. How to know whether we're doing good or wrong? There is a very simple way. Just play. If we play, we can collect the results, average them, and see whether that was a good idea or not. This is the idea of Monte Carlo. Doing simulation and averaging the result to know whether we're going to do good or right. That is nice. We can prove that this is more or less working. It turned out that it's much harder to show that you can use this to enhance the policy. And the other issue is that in order to update anything, you need to wait till the episode ends, because we need to sum the rewards. If the episode have an infinite length, then we are doomed. So we may want to find a way to do a similar update, updating an average. That can be done in an online way like this, but without having to wait till the end of time, not relying on this rule sum over time. And there is a naive idea that that's going to work. That is to replace the gain by an estimate of the gain. We're going to do some kind of bootstrapping, the idea of using an estimator to enhance itself, by replacing the gain in the future by the immediate gain plus an estimate somehow of the gain in the future. I'm writing down here v pi, but we don't know it, so that's going to be an estimate. It leads to a non-lying algorithm that you can write down. Is this going to work? Probably yes, otherwise I won't mention it. But the reason is not because of this heuristic, but rather on a clever analysis of this algorithm as a stochastic approximation one. So I wanted to make a connection between those techniques and stochastic approximation, and that's very important. So we have an algorithm here that is sufficient to do the estimation of the current value function online. And we can extend it to find the best possible policy, either by following a policy and trying to enhance it at each time step, or by computing directly the optimal value function, and then in the end deducing the best policy. This last approach is called Q-learning, because as you can see on the slide, but that I didn't mention, we had to estimate the Q value function conditioning by the state and the action on only the state for a technical reason. The expectation of a max is easier to estimate than the max of an expectation. You can do sampling, and that's it. So what I wanted to tell you is that it's possible to solve this problem of reinforcement learning. There are variations. I focus here on an approach in which we compute those value functions and then deduce the policy, but we can estimate the model and then use the MDP approach. It's not such a bad idea. Or we can do real-time planning, trying to adjust our policy in real time to make it better. Regarding the variation, we can play on the depth, the number of steps we are collecting before we do an update. And we may try to look at the width, the number of actions we consider at each time step. Huge literature on this. Almost nobody is using this in the real world. Why? Because basically I'm assuming that I can store a huge amount of information. I need to have a value, basically, for each pair of states on action. And that could be very large. Are we doomed? Not completely. We can use approximation. And I'm pretty sure this is something that you know. When we have a large set of functions that we want to approximate, we can replace it by a parametric approximation. And that's basically the basis in supervised learning. You do not try to estimate directly the conditional expectation. You try to estimate it through proxies, parametric ones. Here we can try to do the same. What about the parametrization? In the reinforcement setting, there are basically two worlds. The world linear approximation, in which we can prove something, and the world of deep learning, which is going to work. Turned out that it's much, much harder than supervised learning. Because as soon as you add approximation, you need to have some kind of idea of how to measure the quality of the approximation. And it's far from being obvious. Do we want to match the ideal target? Do we want to find an approximate solution of our fixed point problem? Nobody knows. And why? Because most of the time, it's very hard to make a connection between the solution of those approximate problems and the optimal solution. It's a literature in which often the main result is that the algorithm is going to converge. Toward what? That's another question. Quite surprising, but there is a huge places where you can work, if you're interested in this fitting, because it's a world where it's very hard to work in this approximation world. Slightly easier in the classical supervised learning one. That the algorithm, a lot of variation of algorithm, but often they are unstable. Very hard to make them converge, and you have to rely on a set of tricks, I would say. When I'm talking about tricks, it's because often the ideas are coming from the world of practitioners that are building algorithms to estimate those quantities, and they add tricks. Instead of solving one problem, maybe we can slightly change it, and we observe it's better. What I claim is that often, afterward, you can have a theoretical intuition on why it's working by looking at the theory. And now the game, it's better, we're better and better at it, is to use the theory to give heuristic to enhance the algorithm. The last thing I wanted to mention before I jump to the results I claimed I had at the beginning is that we are focused on a very specific point of view in which we're looking at the quality of a solution through those value functions, the expectation of the gain starting from a prediction position. That's perfect without approximation because there is an equivalence between this set of value function and the set of policy. Almost equivalence. So we can move from policy to value function, And an optimal policy is related to optimal value function. As soon as we're making approximation, it may not be the case that the optimal value function within a certain subset is related to the optimal policy. So instead of approximating the value function, maybe it's better to go back and try to approximate directly the policy, which in the end is the objective of interest. But it's funny, this is, I see the state-of-the-art algorithm in the last few years are based on this idea. But that was an idea that was known since the 50s in the control world. You may have heard of Pontryagin approach, this one based on the parametrization of the policy, the action, and the Hamilton-Jacobi one, in which you are thinking in terms of this value function, the interest of a position. Just wanted to say that we can do that. We can compute gradients of the policy, the parameter of the policy with respect to everything, and there are numerical stochastic approximation of all those quantities so that you can, at least numerically, try to compute the derivative of the policy with respect to the world. What we've said before is everything what we said before is useless? I hope no. And the reason is that in all the formula that I know, hidden somewhere, there are those value functions. So we need to estimate them. So there is the idea of plug-in. We try to estimate those quantities, plug them in this formula, and bet on the fact that this is stable enough to work. And it is. And the most efficient approach today are based on this idea that we need to simultaneously parameterize the policy and the value function. And if you do this, you can obtain good results in the end. If you are interested in the proof, the only proofs I'm aware of are in the case when everything is linear, or linear up to a logistic for the policy. And here, the proofs are quite involved and related to stochastic approximation, to stochastic algorithm, and in particular to the idea of two-scales algorithm, in which you move somehow the policy at a slower pace than the estimate of your value function, so that at each time state, morally, the value function are close to the value function of the current policy. If you move them in an arbitrary way, you may diverge. If you are careful and move one piece slower than the other, and the piece that you should move slower is your target, the policy, it's much better. And that's the type of algorithm that are used, for instance, in ChatGPT. You may have heard that they've used reinforcement learning from human feedback in the end, and the final algorithm in which they are tweaking those large language model is based on this idea. I have 5 minutes to talk about results. Just to give you an idea of what one can do with such a tool, or what your students in the future will do, and what you as students are going to do. The first thing is maybe to use them as a tool. And this is exactly how it started for me. With Rémi Besson and Stéphanie Alanossière, we had a collaboration with Necker, the obstetrician from Necker, and they asked us a question of optimization of the prenatal ultrasound exam. Both Stéphanie and I, we know a lot, we're supposed to be experts in image processing. So we thought, well, that's great, we're going to do what we know, image processing. And they said, no, we're not interested in this. We want to be helped to conduct the exam. So This was discovered during the internship of Rémi Besson, which is here. And we say, okay, are you brave enough to change completely the subject and move to something new, a subject for which your advisor will probably be incompetent? And he said yes. And during his thesis, he has been able to use the tool, basic way of using reinforcement learning, but for this specific setting. So you can imagine here that the question is, how can I rephrase my problem, conduct a better exam, as something that you can solve with reinforcement learning? And that's a stochastic shortest path. That's a way of rephrasing this. You want to find the shortest sequence of action to reach a goal, which is conducting the exam well. And the outcome has been a paper. We've been able to publish this result in a mass journal and in a medical one. But the best outcome has been a company. Rémi is now the CTO of Sonio, which has built a product starting from this idea. I'm saying starting because if you are familiar with this startup world, you start with an idea and in the end it's very different. Starting with this, they're building a tool to help practitioners conducting those exams. This optimization that we've seen is a very tiny brick. And they had added a lot of things regarding the way to send the picture in the end, to have a summary of the exam, to measure things, go back to image processing in most of the product of the company. Another thing that you can do when you're working on the field is to say, okay, can I do something better? And this is what also Gary is doing. He's a second year PhD student working with Inde Castel and Emmanuel Lyon. And here the idea was to say, okay, can we go back to a very old problem, the MDP that we mentioned from the beginning, and work on numerical solution of this MDP problem. I've said that this is not practical in any situation, but there are still cases, in particularly in network optimization, in which the size of the matrices are okay so that you can do this in practice. That said, if the matrices are very large, there is a need to optimize the problem. And we've tried to tackle this by using old ideas of good parametrization of the solution, for which we want to be able to prove that the algorithm is sound. That is, we want to have proof of the convergence of the algorithm toward the optimal solution, and at the same time have numerical results showing that indeed in practice it's faster. And this is exactly what Orso is doing currently. And what is interesting is that starting from this specific way of formulating the problem, is done a huge study of benchmarks in this world in order to know whether an algorithm is faster than the other. And as often, it depends. Depending on the style of problem, there are many problems that you can formulate as an MDP. One algorithm may be faster than the other. But what is interesting, what has shown, that its variation is often the fastest one. And the last thing I wanted to mention before I stop is the idea of extension. Maybe you want to depart from the classical way of formulating the problem. And this is what Pierre Clavier has done during the last 2 years and a half. He wanted to add some kind of robustness in this setting. So we made the assumption that the environment is nice, that it's behaving well, and it may be nasty. So here this is the worst case scenario when you have an adversarial force which is trying to make you fail. But you may imagine that in the real world, the world may be changing, maybe evolving in time, and what you learn right now may not be exactly what is true in the future. The idea of robustness, can we find a way to make the learning part robust to a change in the environment? And Pierre has been very brave to tackle this problem from the theoretical point of view. So he tried to measure whether it's harder or not to find a solution of a relaxed problem in which you want to be robust to change in the environment. So very theoretical analysis. And in the end, there is a funny result. It's easier to find a solution of the robust problem than of the non-robust one. It may be surprising, but this is something that you've seen in many places. Often, perturbation, stochastic perturbation, one or another, they're acting as a regularizer. And finding the solution of a regularized problem is easier. So in practice, and this is what is interesting, there is a way to use this idea. That is to have some kind of pessimism in the estimation, quite different from the bandit world. Here, in which you can imagine that if you want to be robust, you have to bet on the fact that the ultimate gain may be lower than what you had planned. So you need to be pessimistic. And what he has shown that in practice, it leads to better solution. So you go faster to a good solution. And if you reduce the penalty, you reduce the pessimism. In the end, you converge to a good solution. And in the world of approximation, and this is probably the most surprising result, you obtain in the end even better result than if you had started with the regular problem. So even if the environment is not changing, when you are doing approximation, it seems that doing this kind of regularization of the problem helps. This may be a reason why, but you know that from theory to practice and from practice to theory there may be a difference. And he is still fighting to know whether this is just a heuristic or if there is a deep connection between those two ideas. Last thing I wanted to mention, you can see that there are 3 question marks here. I've put a date because I'm quite convinced that this time that's going to be okay for the conference. But this is a very hard part of the work of a scientist right now, being able to publish your research. And sometimes you can be very proud of the work of your student, and it fails. Just be patient. And I'm pretty sure that in the end, that's going to be okay. We were joking with Pierre, I've called it the cursed one, because for 1 year it was pure rejection. And for absolutely no good reason. I mean, sometimes there are good reasons for it. And this year, starting in January, everything is going in the right direction. That's why I've put the date. Still an interrogation whether I could put the name of the conference, but we cross our finger and that should be okay. So thank you for your attention. That's all I wanted to say. So if you are interested, there are a lot of books, a lot of lectures. Please feel free to read them. Or, no, without joking, if you are interested in this topic, the best introduction is probably the book of Sutton and Bartow. Very easy to read, because they are hiding a lot of things under the carpet. And if you want to have a better view and more accurate view of what's going on, you have to dwell into much more technical books. And what is funny is that often when we have technical question, you can find the answer in very old books. And that's the truth here. There is a series of books from Bertsekas and Tsitsiklis where 30 years ago, they were using neural networks to solve those problems. It was mostly theoretical at that time for computing reason, but the ideas are there. You just have to understand the vocabulary and the notation. I'm almost on time.
Perfect. Thanks again.
Time for a few questions?
Yes, well, thanks a lot for the very interesting talk, Erwann. So we have time for questions. Maybe I can just start with a small one on the startup you mentioned. I was wondering what were exactly the rewards that you had? Was it to detect some disease, or was it to have the most beautiful picture of the baby?
So for the exact problem Rémi has solved during his PhD, the idea was to reduce the number of interactions, the number of organs that you have to visit before you can make a diagnosis. Because, okay, nobody's pregnant right now. Most of the time, they don't have time to check everything. They are doing their best. But if they see something strange, it's very hard to know exactly what you need to check afterward. And that's exactly what we were doing, suggesting the next object to check, the next organ to check. And this was a mix of modeling, using expert modeling. We were using the expertise of Necker, not by observing the way they are conducting the exam, but just asking them questions on the prevalence of different objects, building some simulators of fetus on which we were training the reinforcement learning algorithm. But as you mentioned, here the reward was fixed by yourself, and that may not be the right one. We're looking at a number of organs. And that's exactly what Rémi has done during his thesis. You can imagine that if you move a product, you should avoid the idea of moving. Look at the head, look at the feet, look at the head, look at the feet. And there is an idea of proximity, of more than one thing that you need to check at the same place. But that's the difference between research and development. Building an idea, a proof of concept on a product, two different things.
Thanks for your talk. Maybe I have a bit technical question. But it's about this robust array.
Yeah.
I was just wondering, you have this uncertainty set U, which is where your transition lives on different rounds. But what do you know about this? Do you know like T0 or the radius?
Okay, so it really depends on the scenario. Most of the time, that the way robustness is presented. So you have an uncertainty set. Here, the scenario Pierre is interested in is the one where you are observing a single value of this uncertainty set, the nominal transition, and you think that the real one is somewhere within the ball. Once again, there are a lot of different modeling. This is a simple one. But realistic, in the sense, it means that you observe a certain world, and you expect that the world is going to change in the future, and you don't want to be good only on this specific world, but on the world that are quite similar. Another setting in one in which you can observe different worlds, and then you can even put a distribution on them.
But this is the one. Yeah, yes.
This sounds similar to the distribution robust supervised learning.
It's always the same ideas everywhere. We are making strong assumptions in the classical analysis of our algorithm. what happens when this is not true? And it's very natural to bet on the fact that the assumption that the world is not changing is false. Same idea in classical supervised learning. What should I do to be robust to some change in the distribution? Then here, what should I do to be robust to some change in the environment?
Questions?